Hi, welcome to the next video. So we'll continue where we left off. This is 6.2.3, the Monte Carlo method. Methods. Okay, so example 6.11. So this is, we're going to study the Monte Carlo method. For evaluating definite integrals. So Monte Carlo method for evaluating definite integrals. Let's say phi of u is continuous on a less than equal to u less than equal to b and is bounded below and above by 0 is less than equal to 5u less than equal to capital M. Okay, so this is the Monte Carlo method for evaluating definite integrals. So we're going to find a definite integral or estimate it by making random choices. I'll show you what I mean. So let's say 5u is continuous on this interval and is bounded below and above by that. Consider the experiment S. Consider the experiment S, where a random u comma v is selected from a less than equal to u less than equal to b, 0 is less than equal to v less than equal to capital M. Okay, so let's look at the picture. Let's say you have this axis and this axis. Okay. And so let's say u is going from A to B. So this is the u axis. U is ranges from A to B. Little v ranges from 0 to capital M. And so there's A here, here's B here, here's capital M there. Okay, so you have this area here. So u comma v is in that box, okay? So we're going to select a u comma v at random from this box, where u is ranging from A to B, and v is ranging from 0 to M. Okay? We're going to let capital X be defined as let capital X be the random variable defined as x equals 1 if the point is below the curve of 5t and 0 otherwise. Okay, so x is 1 if the point is below the curve 5t and 0 otherwise. Okay, so we're going to select a point at random u comma v, and so let's say we think of 5t, right? 5t ranges from 0 to capital M, where u is between a and b. So phi of u is a continuous function, like that. So that's phi of t. phi of u, sorry. That's phi of u, where u is from a to b. Okay, so it's a continuous function, and it's bounded above by capital M and bounded below by 0, and it's defined from a to b. Okay? So if u comma v is a point in here, right, then x of that point would be 1. So here, x of that point would be 1. Here, x of that point would be 0. Okay, so x is 1 if the point is below the curve phi of phi. So here's phi, so the point's below it, x is 1 here, x outputs a 0 for that point there. Okay. So let's observe that. So observe that the probability that x is equal to 1. So the probability that x is equal to 1 is well, what are the chances that the point is below this curve, right? What are the chances the point is below that curve? It's just the area underneath that curve. Right? And what is the entire space we're considering? It's the space of this entire rectangle. And so it's the area of the rectangle. So the probability that x is equal to 1 is the area under the curve divided by the total area of the rectangle. And so what is that? The area under the curve is the definite integral from a to b of phi of u to u, divided by the area of the rectangle, which is capital M times b minus a. So the probability that x is 0, is 1 minus the probability that x is 1. And so, okay, that's something. Okay, so also the probability that x is equal to 0 is 1 minus the complement of the event x equaling to 0. The only other value x takes is 1. So if x is not equal to 0, then it's equal to 1. So the probability x is equal to 0 is equal to 1 minus the probability x is equal to 1. Okay, so the conditions of this experiment is the same. Okay, we're choosing a point u comma v, right? And if it's below the curve, the value of x is 1. And if it's not below the curve, then its value is 0. So all that's the same. So we have these observations still here. We have this picture. In the book, there's a similar picture, and it's figure 6.1 in this section. So figure 6.1 is similar to that. This axis is the phi of u axis. Let's say, because that's the value of phi of u. Okay, that's capital M. Good. Okay, so the expected value of x is equal to 1 times the probability x is equal to 1 plus 0 times the probability x is equal to 0. Right? It's the sum of over all possible values of x times f of x. So it's 1 times the probability x equals 1 plus 0 times the probability x equals 0. So since this is 0, that product is 0. That goes away. Now the probability x equals 1 is that. 1 times it is itself. So you get that definite integral divided by capital M times b minus a. That's e of x, right? So e of x is equal to that fraction. And so that implies that the definite integral from a to b of 5u du is equal to capital M times b minus a, this thing, times e of x. Okay, and so all of this was to get this equation here, to get this stuff up here. So I can erase all of this. So we're going to need this space later. So I'm going to erase this here. And so let's keep going. So we have those two equations there. if we perform the experiment, capital S, n times, and n is large, and letting x of I equal to the value of x on the I performance of S, then by the strong law of large numbers, we get. So first, okay, so we perform the experiment S, capital S, that's the name of the experiment, n times, meaning you have the, right, so you have the curve, right? Okay, I guess I'll redraw this. You have the u-axis, you have the values of u from A to B, you have phi of u, whose maximum value on that interval is capital M, so that's phi of u, right? And if you take a point u comma v, right, it could be either below the curve or above the curve, right? That's the experiment S. The experiment S is it's choosing a random point in that rectangle, and x is 1 if the point is below the curve, and x is 0 if it's not below the curve. Okay, so we perform that experiment n times, and n is large. Okay, so x of I is the value of x on the I performance of S. Then by string of large numbers, we get, what we should get is that if we add up the values of x in all I performances of the experiment and divide by the number of times we perform the experiment in n, that should be approximately E of x with great probability. Okay, so we're not saying that the sum of the x values divided by n is approximately the expected value, but we're saying that the sum of the x values over n is approximately the expected value with great probability. So it's most likely, it's with very high probability, the sum of the x values divided by n is close to the expected value. Okay, there's very little chance that the sum of the x values divided by n will not be close to the expected value. Okay? All right. So, therefore, the integral from A to B of phi of u du, which is this guy, is approximately m times b minus a times e of x. And e of x is the sum over the I from I equals 1 to n of x of I divided by n. So I'm just replacing the expected value here with this, and since they're approximately the same with great probability, this integral is approximately that with great probability. So it's highly likely that this definite integral is approximately the same as capital M times b minus a times the sum of the x values in n performances of the experiment S divided by little n. Okay, and so what is this saying? So you reach an interesting conclusion here. If this is the situation, and let's say you choose a really large n, like 1,000. Let's say you can find a random way to choose a point in this rectangle, right? 1,000 times. Then what this is saying is that it's very likely, it's not definite, but it's very likely that if you randomly choose 1,000 points in this rectangle, take the sum, right, where you get a 1 if that point is below the curve and 0 if it's above it. Add up the values of x in those 1,000 times you randomly choose a point in the rectangle. Divide it by 1,000, the number of times you chose a point. So take the sum of those values divided by 1,000. Multiply it by capital M, which is the height, times b minus a. And you'll get a number that is very close, approximately, the definite integral, the area under the curve. And so you can approximate the area under this curve, or that value of that depth interval, by randomly choosing points a high number of times in this rectangle. Which is weird, but by the strong law of large numbers, that's what we're saying, okay? So again, we're saying that if we randomly choose a point a very large number of times in this rectangle, and we assign a 1 each time it's below the curve and a 0 each time it's above it, the sum of the ones or zeros divided by the total number of times you do it, times capital M times B minus A, that product is very close to the area under the curve. Weird. With great probability, it's very likely they're close. Very unlikely they're not close. And so you could be sure of your estimate with a high degree of certainty. Okay? Okay, and so that's the conclusion we reach from all that. And so that's called the Monte Carlo estimate of a depth interval. We can estimate this integral with that value. And we're very likely it's a good estimate. High probability. So I'm going to leave that conclusion on the board, and then we're going to use that conclusion to solve the next problem. Okay, so example 6.12. It's the Monte Carlo estimate of depth interval from 0 to 1 of e to the negative u squared over 2 du. So phi of u is equal to e to the negative u squared over 2. Okay, so here, the phi of u here, that phi of u is that function here. So if I want to estimate the value of that depth interval, I'm going to let phi of u be the integrand. Now I'm going to let capital M be 1. And I'm going to let little a be 0 and little b equal 1. And so it doesn't specify what the values of capital M or b or a have to be. And so I chose capital M to be 1. I chose little a to be 0. And I chose little b to be 1. That way it's 1 times 1 minus 0. So you just get 1. Okay? So the situation we're making is that you have the u-axis, you have the phi of u axis, you have a range of values from little a to little b. Well, a is 0, so it's from 0 to 1, because that's a is 0, b is 1. And then the maximum value is capital M, which is 1. So you have this square, all right, 1 by 1 square. So you have that square, and then you have phi of u, which is a continuous function. Right, that's phi of u, defined from 0 to 1. And so now we're going to estimate this area. Oh, it's e to the phi of u is e to the negative u squared over 2. Right, so however that graph looks, e to negative u squared over 2. Take the area underneath it. When u is 0, the value is 1. When u is 1, get e to negative 1/2. You get 1 over the square root of e. So it's some value smaller than 1/2. And so if it's 1/2, you have 1/4. 1/8, 1 over the 8th root of e. So it's 1 over e, 1 over the square root of e here. And then when it's 1/2, it's 1 over the 8th root of e. Right, so then this thing, the square root of e is larger than the 8th root of e. So 1 over the 8th root of e is greater than 1 over the square root of e. So this is, so what I'm seeing is I think there's going to decrease, somehow decreasing this function. It's in my intuition tells. So let me take an educated guess and say it looks something like that. And so let's look at the region underneath that. And so then that's going to be phi of u, which is equal to e to negative u squared over 2. Okay, and so let's look at the region there. So definite integral from 0 to 1 of e to negative u squared over 2 du by the Monte Carlo S. So so the Monte Carlo estimate, so this thing is e of x, right? This thing, remember, is equal to e of x. And so if this is all 1, then this is equal to e of x. And the definite integral from 0 to 1 is approximately that, because this is approximately, this is approximately e of x, which is why this thing is approximately that. So, this definite integral is equal to capital M times b minus a times e of x from what I mentioned before. It's equal to it. Then when you replace e of x, this is an approximation of that, which is why this is an approximation of that. And so since this is 1 here, well, capital M is 1, b minus a is 1, so this is equal to capital E of x. And then the definite integral from 0 to 1 of e to negative u squared over 2 du, that's approximately, so then that's approximately, this is 1, and so that is approximately that sum. So using the random numbers in table 4 in appendix C, okay, then what happens is that this definite integral is approximately the sum from I equals 1 to 17 of x of I over 17. And so that's equal to 15 over 17, because the decimal is 0.8824. Okay, so the random number table in the random numbers in table 4 in appendix C tells you that this sum is 15. So you get 15 over 17, which is 0.8824. Okay, and so this is the Monte Carlo estimate of that definite integral. Okay, Okay, so the Monte Carlo estimate is 0.8824, and the value using the table is 0.8555. Okay, so it's close. So when we estimate the value, it's 0.8824, and when we find what the value is, the table tells you it's 0.8555. Okay, so we see in this example how we can use the Monte Carlo estimate to estimate the value of a definite integral with great probability. It's likely they'll be close, and in this case they are. The first decimal point is the same, the 10th place is different, but it's not too far off. Okay, so that is the end of 6.2, and so let's keep going. Let's go to 6.3. Okay, so 6.3, the mathematical expectation of a function of a random variable. So 6.3.1, function of a random variable. So definition 6.3. So let x be a random variable. Defined on the sample space. So let capital X be a random variable defined on the sample space S. Let G be a real value function defined for values X that are possible values of capital X, or negative infinity less than x less than infinity. Okay, so let G be a real valued function defined for values of x, values x are possible values of capital X. So G is just a real value function defined on all possible values of capital X. Okay, or for any real number little x. The random variable g of x, g of capital X, is defined on capital S as follows. For each little s and capital S, for each little s and capital S, g of x of s is equal to g of capital S x of s. Okay, so G is a real value function. So what that means is that that X is a random variable defined on your sample space S. X takes on values, and then you just input those values of X into your function G. Okay, so for whatever values X gets, whatever values of X you get, you just plug into the function G. And that's what this is. Okay, so G of X of S is equal to, you take a value of X and you plug it into the function G, and it outputs a real number. Okay, and so that is the definition of the random variable capital G of X. So G of capital X, the input is a value of capital X and the output is a real number. Okay, and so this is a random variable. Okay, but here, so wait, let me just explain why. So if you have the function X, if you have the random variable capital X, this is the random variable capital X, and this is the event S. Okay, so if you have an event S and you input it into your random variable capital X, the output, right, is the value of X. Okay, now if you take that value of X and you input it into the function G, okay, then it will output a real number. Okay, and so G of X of S is the composition of those two functions, where you start with an event and you input it into the function, into the random variable G of X of S. And then the output is that real number. So the composition of those two functions is G of X of S. Okay, and so this is a random variable. It takes it's a set function, and the input is an event, and the output is a real number. And so G of X of S is also a random variable. So it's called G of capital X. So let me put G of capital X here as the name of it. Okay, and so that is a G of capital X is a random variable. It's a function, right? It's a set function. The inputs are events, subsets of the sample space, and an output is a real number. It's a composition of X and then the real value function, little g. So G of capital X is also a random variable. X was a random variable, and G of capital X is also a random variable. And it's defined by, again, this equation. G of X of S is equal to G of X of S. Okay, so my goal here was to show you why G of X is called a random variable. Okay, it's not just G; it's the composition of G composed with X. Okay, so let's look at an example. Let S be the experiment of rolling two dice. And let capital S equals the set of ordered pairs I, j, such that both I and j are between 1 and 6 inclusive. B, the sample space for capital S. Okay? The capital X equal the sum of the values of the two dice. So that x of I comma j is equal to I plus j for I comma j in capital S. Okay, so this is what this is saying. If you take a dice, you're rolling two dice. So I'll draw two of these boxes. These are dice. Okay, and so these values go from 1 to 6. These values go from 1 to 6. And so we're expressing the sample space, the set of all outcomes of this experiment of rolling two die, as being this set S. Right? That's the set of all ordered pairs where the first member is the number that appears on the top of this dice, and the second member is the number that appears on the top of that one. Right? So the set S, which is the set of all ordered pairs I comma j, so it's that both I and j are between 1 and 6 inclusive. That set is the set of all sample points of this experiment. I is one of the numbers 1 to 6, the first roll, and j, number 1 to 6, is the second roll. So the set of all possible ordered pairs like this, that represents all the ways to roll two dice. 6 choices here, 6 choices here. There's 36 sample points in this sample space. Okay? Capital X is a real valued function, and it's a random variable that sums the two values of the dice. So for instance, if you rolled this dice and got a 1, and you rolled this dice and you got a 4, x of 1 comma 4 would be the sum of those two values, the sum of the two dice rolls, and it would be 5. So x is taking as an input a sample point in the experiment, which is 1 comma 4, which 1 is the outcome of the first roll, 4 is the outcome of the second roll. It's taking a sample point in your experiment, in your sample space, and it's outputting the sum of the two numbers, the first member of the ordered pair plus the second of the ordered pair, which represents the sum of the two rolls. Okay? So here, so now x of I comma j is equal to I plus j. And so that is a real valued random variable that adds up the sum, adds up the values of the two dice rolls. Well, oh, sorry. Okay. Well, it kind of is that. No, it's just so x is just a random variable that represents the sum of the two dice rolls. So x of I comma j is equal to I plus j. So if you take a sample point, x adds up to two rolls of the die, I plus j. Okay. Let g be the function g of x is equal to x squared for negative infinity less than x less than infinity. What is g of x? So let g be the function g of x equals x squared for real number x. What is g of x? Okay, so g is a real valued function. Okay, so now let's see. So g of x is a real function. G is a real function where it takes a value of x, which is the sum of the two dice rolls, and it squares that number. So, for instance, if you would take 2 comma 3, which is the sample point of getting a 2 in the first roll and a 3 in the second roll, x is a random variable that takes the sum of those two dice rolls and gives you a 5. Okay, so 2 comma 3 is a sample point, is an outcome of the experiment. X takes the sum of the two rolls, and so x of 2 comma 3 is 5. And then g of x of 2 comma 3 takes the sum, takes the value of x, which was 5, and squares it. And so you get 25. Okay? So x gives you the sum of the 2 dice rolls, which is 5. And g of x takes the sum and squares it. So g of x of 2 comma 3 is 25. Okay, but in general, you can define your function g of x of I comma j for an arbitrary sample point I comma j in the sample space capital S as being g of x of I comma j. Okay, and what that does is, remember, x of I comma j is I plus j, so this is g of I plus j. And g of I plus j is just taking the sum I plus j and squaring it. And this is for any I comma j in the sample space capital S. Okay, so g of x is the random variable that represents the square of the sum of the values of the 2 dice. Okay, so g of x is the random variable that represents the square of the sum of the values of the 2 dice. Okay, so maybe another example of how x and g work. All right, let's say you take a roll of the dice, 4 comma 3, and that's a sample point, right? So this is a sample point in capital S. X of 4 comma 3 would be the random variable that adds up, which is the sum of the 2 dice rolls. So that's 4 plus 3. That's 7. So x takes the sum of the 2 dice rolls. It's really inputting just one sample point, right? Because 4 comma 3 is one sample point. But x is adding up the first and second component, which represent the results from the first and second roll of the die. So x of 4 comma 3 is 4 plus 3, which is 7. Now g of x of 4 comma 3, well, is g of x of 4 comma 3. What that does is it takes what x, the value of x for the sample point, which was 7, and what g does to that number 7, the value of x, which is 7, it squares it. And so it's 7 squared, which is 49. But in general, right, because of what we wrote at the bottom, if we start from the beginning, 4 comma 3, g takes the sum of the values and squares it. And so 4 plus 3 is 7, and 7 squared is 49. And that's what we got here by applying the formula we wrote over there. Right, g of x of 4 comma 3 is g of x of 4 comma 3. X of 4 comma 3 is 7. G of 7 is squaring that number, 7 squared, which is 49. So that's a second example of computing what this random variable g does. Okay? It squares the sum of the values of the 2 dice. So that's example 6.14. Okay, so for the function g of x we just described, we can write it as x squared. Okay, so the function was g of x equals x squared. So instead of writing g of x to represent the random variable, you can just write x squared. Okay, it's a real valued function on x that squares the value of x, right? And so we say g of x is a random variable. Instead, you can just say x squared is another random variable without calling it g of x. So you don't have to say g of x is x squared. You could just say x squared is a random variable. Okay. Okay. So similarly, if g of x is equal to a naught plus a1x plus a2x squared plus dot 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 plus an x to the n, then g of x is written as a naught plus a1x plus a2x squared plus dot 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 plus a sub n x to the n. Okay, so what this means is, right, if you were to find your g of x as a random variable to be equal to that polynomial, right, instead of defining a random variable g of x, which is that, you could just say that this is another random variable. Okay, so you don't have to say g of x is a random variable where it's equal to that. You could just say this polynomial is another random variable, given the x in it, in the expression, is a random variable. Okay, so you can write that, you can say that's another random variable. All right. Okay, so I just want to make that point. This is also another random variable. Let's do the next section. So I'm going to erase this. Let's do the next section. Okay, so 6.3.2. The mathematical expectation of a function of a random variable. Okay. Just give it a pen. Okay, so this one would be quick, easy to read. Theorem 6.2. Let capital X be a random variable with probability function of x. Let g be a real value function the real value function defined for values x that are possible values of capital X, or for negative infinity less than x less than infinity. The mathematical expectation of the random variable of the random variable g of x is the quantity e of g of x, which is equal to the sum over x of g of x f of x if x is discrete. That's equal to the integral from negative infinity to infinity of g of x f of x dx if x is continuous. Provided the series converges absolutely if x is discrete, and the integral is defined if x is continuous. Okay, so I'll stop. I'll let you read this and write things down. Okay, so 6.3.2 is the mathematical expectation of a function of a random variable. So theorem 6.2 says if let capital X be a random variable with probability function f of x, let g be a real valued function defined for values x that are possible values of capital X, or for any real number little x. That's what that means. The mathematical expectation of the random variable g of x is the quantity e of g of x, which equals that if x is discrete and that if x is continuous. Provided the series converges absolutely if x is discrete, that means the sum of the absolute values of its terms is finite. That's what it means for the series to converge absolutely, right? That series converges absolutely if the sum of the absolute value of its terms is finite. That's if x is discrete. And the integral is defined, and so if x is continuous, the expectation is equal to that improper integral if the integral is defined, meaning when you compute it, you get a finite number. Okay? And so this defines, again, the mathematical expectation of the random variable g of x, right? We have the expected value of a random variable x. This is the expected value of the random variable g of x. Okay, so again, we have the expected value of x. This is the expected value of g of x. G of x is also a random variable. I was showing you before by the picture. And so g of x is also a random variable, so it also has an expected value, and it's different than the one for x. And so this tells you, this defines the expected value for the random variable g of x. Okay? And we have to do it for both x when it's discrete and when it's continuous. And so depending on whether it's discrete or continuous, you get this if it's discrete, that if it's continuous. Okay? But you need the sum to be finite, and you need this improper integral to be finite. If you're going to define the expected value to be a sum or integral, you want the sum or integral to converge to some finite number. And so that's what the assumptions again are. Series converges absolutely, the sum of the absolute values is finite, and that the integral is defined if x is continuous, and so you compute it and you get a finite number. Okay? Okay, so that's the definition of the expected value of g of x. Okay, so I'll leave this up again for a little bit longer so you can read it and write things down. You can pause the video at any time if you need to take notes of something. You can watch the video again also.